Yeah.
Anyway, what was I going to say?
Well,
I'm not going to see it.
All right.
Oh, yeah, she's not going to.
So yesterday,
I had you.
or not yesterday. Yesterday I was at home watching football all day. But on
All day.
all day. On Friday, we talked about composition of functions. Any questions on that stuff?
No, but I have a good question.
Yes, go right
Do you
ahead.
have a quiz on
I had a
it?
guess.
Great question. Yes, there's a quiz Wednesday, but it's only on last week's material. It doesn't include anything that we're going to do today or tomorrow.
Great, okay, thank you. I thought that was just like one of those 15 minutes and then we play games.
Correct. Yes.
Cool. Like you said, too.
All right. Any other questions?
Yeah, what do you guys?
Okay, so today we're going to talk about inverse functions.
So what's the other option?
Really?
Good
It's
job.
gonna be whatever. I don't use the content.
Inverse functions. Okay, so two functions are inverses of each other. All right, two functions are inverses of each other if they undo each other. Okay. So, for example, if I have the function y equals x plus 2 and y equals x minus 2, it makes sense that these functions undo each other, right? Like if you add 2 to a number, the way that you would undo that is you would subtract 2, and vice versa. If you subtract 2 from a number, then the way you would undo that is you would add 2, right? Right. Or if I had something like the square root of x, the way you would undo that would be to square it, right? So these two functions would undo each other. That makes perfect logical sense, right? Okay, so there's actually a way you can more define this, so you can define this in a way that's a little more analytical rather than intuitive, like, yeah, it's obvious they undo each other.
I was thinking that you were saying that square root of x undoes x.
Oh, I got you. No, I'm saying like these two are inverses of each other, and these two are inverses of each other. Yeah.
Just gotta be confused.
No, that's a good question. Okay, so so more analytically here then, f of x and g of x are inverses if f of g of x equals x and g of f of x equals x for all values of x. So this is just saying if you compose the two functions, if you do one and then you take that result and you do the other one, you get exactly what you started with. That's what this is saying, like mathematically, in terms of mathematical symbols, right? It's saying if you do g to this x value, and then you take that result and you do f to it, you get the x value you started with. And this is the same thing, but just in the opposite order. So they undo each other. So if I test that for like one of my examples up here, like if I test it for, suppose f of x is equal to x plus 2, x plus 2, and suppose g of x is equal to x minus 2. I could test to make sure that they're inverses by doing this to them. I could say f of g of x. If I do that, I get f of, remember you start from the inside and work your way out. This would be f of x minus 2, which would be x minus 2 plus 2. I just substituted x minus 2 into this function for x right there. I substituted in right there. And I get x minus 2 plus 2, which is x itself. So far, so good. G of f of x would be g of x plus 2. So now I'm going to go to g, and I'm going to replace this x value with x plus 2. So I get x plus 2 minus 2, which is x. Awesome. They undo each other. I mean, it was kind of obvious to see that right from the beginning, but it won't always be that obvious. So that's how you can test to see if functions are inverses of each other. A more interesting question would be, if you have a function, how can you find its inverse? So that's what I'm going to focus on today. So find the inverse of a function. Find the inverse of a function. You just switch x's and y's. That's all you do. So, for example, if the function was just a collection of points, if the function was, suppose the function was f of x, and I'm going to just give a table of values. Okay, so I have x, f of x. Suppose the points are 0, 3, 2, negative 1, and 4, 1. Suppose that's f of x. Then the inverse, and you should know that the symbol for inverse is just like negative 1 power. F inverse of x would be 3, 0, negative 1, 2, 1, 4. I just switched x's and y's. So this symbol right here means inverse of f of x. That's what that notation means. And you can test this pretty easily. Like if I take a number like 2 and I do f to it, I get negative 1. Then if I take that result and I do f inverse to it, I get 2, back to what I started with. So it makes sense, right? If I started with 0 and I do f to it, I get 3. And then if I take that result and do f inverse, I get 0, the x value that I started with originally. So that test that I did up here would definitely work. Like if I did f composed with f inverse of x, I always get x, whatever I started with, okay? And vice versa. If I started with the number here, like say I started with 1, if I do this function to it, I get 4, and then I take that result and I do this function to it, I get 1, the same thing I started with. Okay, so that test definitely works. Find the inverse of a function, you just switch x's and y's. So if it's a list of points, super easy. If it's an arrow diagram, super easy. You just switch x's and y's. Arrows will be going the other way. Okay, instead of going from 0 to 3, it will go from 3 to 0. Make sense? Okay, so the ones that are a little more interesting would be the ones that are either graphs or the ones that are like equations. Okay, so what if it's an equation? So what if you have something like f of x equals 2x plus 1? Okay, so here's the process. You're still going to switch x's and y's. That's still what you're going to do, switch x's and y's. Now, in a situation like this, there aren't any y's, but there kind of are, because f of x is really just another way of writing y, right? So this is really the same thing as y equals 2x plus 1. So that'll be the first step. Make sure that you have x's and y's. If you don't have y's, then you got to replace whatever the name of the function is with y's, because that's what a function really is. It's giving you y values. Okay? Then you switch x's and y's. So x equals 2y plus 1. Just switch x's and y's. Everywhere there's a y, put an x. Everywhere there's an x, put a y. And then it's just a matter of solving for y. That's it. I'm going to solve this for y. Solve for y, which would give me 2y equals x minus 1, and y equals x minus 1 over 2. This is f inverse of x. Right here. And it seems logical, right? Like, think about what this function does. It multiplies things by 2 and then adds 1. If you wanted to undo that, you would subtract 1 and then divide by 2. That's what this is saying to do, right? To undo something, you do the inverse operation. So you have to subtract 1 and then divide by 2. Subtract 1 and then divide by 2. And same thing with this. The net effect of this function is it subtracts 1 from things and then divides by 2. If you wanted to undo that, you'd have to multiply by 2 and then add 1. That's what this is saying that you do. You multiply by 2 and then add 1. So again, this might seem a little obvious, like you could sort of figure it out without doing this process. But if you do the process, it's just as easy for more complicated functions as it is for easy functions. So I would recommend that you do the process every time. Okay? So what if the original function was h of x equals, suppose it was something like, complicated here. How about this? What if it was x minus 3, parentheses, x minus 3 cubed plus 1 divided by 7. I mean, just intuitively, I know that there's going to have to be a times 7 somewhere to undo the multiplying by 7 or dividing by 7. I know there's going to have to be a minus 1 somehow. I know there's going to have to be probably like a cube root. That's how you undo a cube, right? And then there's going to have to be a plus 3. But figuring out how all those things fit together is complicated unless you do the process. So let's do the process. So the process is replace this with a y, x minus 3 cubed plus 1 over 7. Interchange x's and y's. Everywhere there's an x, put a y. Everywhere there's a y, put an x. So this would be x equals y minus 3 cubed plus 1 over 7. Now just solve for y. So if I'm solving this for y, I would first multiply by 7. Then subtract 1. 7x minus 1 equals y minus 3 cubed. What do I do next? Cube root, I agree. So this would be cube root of 7x minus 1 equals y minus 3. And then finally, add 3. So y would be cube root of 7x minus 1 plus 3. That's the inverse. This is, if the original function was h of x, this is h inverse of x. Did you guys do this last year in arithmetic? No? Anybody remember ever doing this?
After doing before, so we can.
Oh, that's true.
Swapping x with y.
Okay, good. Let's try another one. Let's try a hard one. What about something like f of x equals 6e to the x? So y equals 6e to the x. If you switch x's and y's, you get x equals 6 to y. What do I do now? Not yet.
Divide by 6 and then
Divide by 6 first, then natural log. Yeah, so this would be x over 6 equals e to the y. Now I can ln both sides. And I get y equals ln x over 6. That's f inverse of x in this case. Remember, the inverse function of a logarithm is an exponential. The inverse function of an exponential is a logarithm with the same base. So what if I had a different base? Like what about something like, what if it was f of x equals 2 to the x minus 4 power? So y equals 2 to the x minus 4. Switch x's and y's. So x equals 2 to the y minus 4. Now, to get that out of the exponent, that y minus 4 out of the exponent, I have to log both sides, but it's log base 2. Right? So you log base 2 x equals log base 2 of 2 to the y minus 4. But these things here would just cancel. Right? That's what happens with logs and exponentials with the same base. They cancel each other out. So you get log base 2 of x equals y minus 4. So y would be log base 2 of x plus 4. That's the inverse. This is f inverse of x. Does that make sense? All right, this one's definitely more challenging. What about something like g of x equals x plus 3 over 2x minus 1. So what's different about this one is x appears twice. If I look at all the other examples I gave you, the original function only has x in one spot. One spot, right? One spot. But down here, x appears twice. And what that means is when you switch x's and y's, y is going to appear twice. So if you're solving for y, it becomes a little bit more challenging. So y equals, it's the same process, it's just the algebra is a little harder. Then switch x's and y's. So x equals y plus 3 over 2y minus 1. Now I need to solve for y. So how do I do that? How do I solve for y? Okay, we could cross multiply. That's a good idea. So we would have x times 2y minus 1 equals y plus 3. And then I could like distribute that. 2xy minus x equals y plus 3. Okay, then what?
Take x out.
Say it again?
Use the like factor x out of the 2.
Well, that would give me what I just had,
Oh, yeah.
right? So I don't know if that would help. There's a little bit of an algebra trick involved here. What you could do is you could get the y's on both sides, 2xy minus y, and get everything that doesn't have a y in it on the other side, and then take out a y. So, because our goal is to get a single y, right? So now we can get a single y by factoring out a y. So y would just be x plus 3 over 2x minus 1. That's the inverse. The original function was g, so this is g inverse. So that's the little algebra trick if it's a rational function like this. Let me do another one like that.
So it's basically basically. Yeah, it's literally the same as when you switch there.
Oh, that's weird.
That is weird.
That's coincidental.
Okay, don't get used to that.
Wow, why did that turn out that way? It won't always turn out that way. I'm trying to think why it did. Mind's blown. Oh. Never know. All right, let's try another one. Hopefully it won't turn out that way. That's coincidental. It's not going to be that way. How about f of x? What if it was like x over x plus 1? Like that. So y equals x over x plus 1. x equals y over y plus 1. So let's do the same thing. I'm going to cross multiply, so I get xy plus x equals y.
And then you switch the y at the end.
It is going to be the same. Oh, no, it's not. It'll be different. It'll be different this time. So if I group together the y's, yeah, it'll definitely be different. And then factor that out, y. I get negative x over x minus 1. That's definitely different than what I started with. This is f inverse.
I wonder if there's some sort of like weird.
Well, all right, so let me just talk about one more thing, and then we'll come back and talk about why that one's inverse happened to be itself. Because there is kind of a reason, but it's just super weird that I just happened to just come up with one like that, just making up a problem. That seems like it could be kind of rare. So let's talk about one more thing, and that is, what if the function is a graphical function? Like, what if I have a graph, and I want to find the graph of the inverse, okay? So what if I have the function that just looks just a random, like, kind of squiggle like this, and suppose that's f of x, and they want us to graph f inverse of x. Well, if we were to switch x's and y's, which is what you always do to find inverses, right? You switch x's and y's. If we were to switch x's and y's graphically, that means if I have a point here whose coordinates are, let's say, -1, 2, right? If I were to switch x's and y's, then that point would now become 2, -1, right? It would be like 2, -1. Its inverse point would be like there. You agree? 2, -1, right? And we'd have to do that for every single point. Well, let's just think about what that really means graphically, though. What you're really doing, if you're moving this point to there, is you're just reflecting over the diagonal line, which is y equals x. Makes sense, right? If you have this diagonal line, y equals x, doesn't it make sense that reflecting over that diagonal line is going to make everything that was an x a y, and everything that was a y an x? Makes sense, right? So what you're going to end up with graphically is you're going to end up with something that's just a reflection over this line. So it's going to kind of look like this. It's going to be symmetric over that diagonal. This is going to be f inverse. So this would be true for any graphical function. If I had a function whose original graph was, say, like a parabola, like that, then its inverse would just be a parabola that opens sideways. It would be kind of like that.
So in like how are they overlap? Is that how you get the one that like is the exact same and then just like
Yeah, so a function whose inverse is itself would have to be a function that is originally symmetric over the diagonal. Like, for example, 1 over x. 1 over x looks like this, right? If you draw the diagonal and reflect over that diagonal, you get itself. So if this is the original function, f of x equals 1 over x, then f inverse of x is also 1 over x. So it must be that that example that I made up is symmetric over the diagonal. I mean, we could investigate a little bit. Like if I look at the original problem here, x plus 3 over 2x minus 1, and I draw a little picture of it on my graphing calculator. So let's see. I mean, we could graph this using like the analytic methods that we learned like in the last chapter, but that takes forever. So this is quicker. So x plus 3 divided by 2x minus 1. So if I graph this, And I'm just doing like a normal zoom. I mean, you can see it's kind of like the same as 1 over x, it's just shifted somehow. And it must be that if I drew in the diagonal, like if I draw the diagonal on the same set of axes, y equals x, I mean, you'll see it's a graph that's symmetric over that diagonal. So that's why its inverse was itself. Like I said, like to just make one up and have it be that way, I should go buy a lotto ticket today or
So
something.
like if something like base is 1 over x, and then it's not shifted like vertically at all, then it should be.
Yeah, yeah.
Okay.
Yeah, trying to think, do we have other functions, like other of our basic functions that are symmetric over the y-axis? I can't think of any. Or symmetric over the diagonal? I can't really think of anything, other than y equals
Y
x
equals
itself.
X, right?
Yeah, y equals x itself, or y equals negative x would definitely, that would be true for.
Yeah.
Yeah.
But-
Okay, all right, so on the homework, it's on Delta Math and it's just inverse functions, but some of them you have to do algebraically by switching x's and y's to solving for y. And some of them you have to do graphically. They'll give you a graph and you just have to take, I think it says like 3 or 4 points and graph the switching x's and y's. Like if the point is at 2, -1, 2, you just have to plot the point 2, -1. And you have to do that for like 4 different points, I think, or 3 different points, and then it'll graph the inverse, and then that's it. Does everyone understand what I mean? Okay. I'm gonna stop recording.
So I saw him say, I am not.
That's what I said.
But I can do it the other way.